If it's at equilibrium, then it doesn't not only accelerate linearly, because sum of the forces is equal to 0, but it doesn't rotate and accelerate angularly either, because sum of the torque is equal to 0. So this is now our new definition for equilibrium. Before, in chapter 5, chapter 6, the concept of equilibrium was mathematically Newton's first law, because we were only doing translation. Now that we're considering rotation and torque, we need to add another condition, which is that sum of the torque is equal to 0. So now this is our new definition for equilibrium, which means now we have one more equation in 2D that we can work with. Remember, Newton's equation from the vector notation is one equation in 1D, two equations in 2D, three equations in 3D. For the torque, if you're doing one-dimensional problem, you cannot use a torque. But if you start doing 2D problem, which is what we're going to be doing, then the torque equation will give you one scalar equation, clockwise, counterclockwise. And the axis rotation is perpendicular to the plane. If you're doing 3D problem, then you're going to pick up 3 torque equation. Therefore, you're going to have 6 equations, which means you can have up to 6 unknown. In this class, we will focus in 2D problem. Therefore, you can always write and obtain 2 scalar equation as before, chapter 5, chapter 6. And now you will be able to pick up one more. So now we're going to be dealing with a 3x3. So let's go over a bunch of static equilibrium problem. And what I will do is just set up every one of those problems until we get the equation, and I will leave it to you to solve those 3x3. The rest is just math. So again, please, hopefully you did invest in the calculator, into which now you can just enter your 3 equations, bing, bang, boom, find the button that says solve, or whatever it is, so you don't lose time. Because remember, if you go further, whether you go E in 211 or you go C and ME in 270, 271, you will be expected to have one of those calculators. Otherwise, you would never have time to finish any test. So hopefully you did obtain one over break, so that the rest of the semester would be easier on this, math-wise. So let's look at this problem. Let's imagine that we're given FA, such as, let's say FA is equal to 2 Newton. And we're being told that the system is in static equilibrium. And the purpose of the game is to figure out the magnitude of FB, FC, and FD. So again, as you can see, static equilibrium in 2D will give us 3 equations, which means you can be asked up to 3 unknown. If there is more than 3 unknown in a system of equilibrium, you know something is wrong. Maybe you missed something in the whatever problem that simplifies it. You can never have more than 3 unknown. Again, if you're doing a 3D problem, you can have up to 6 unknown. So we know that Newton's first law in translation form can be applied. So if we use the coordinate system given to us, and we only consider those 4 forces, FA, FB, FC, and FD, by neglecting the mass or any other forces, then it's just apply Newton's first law. That's back to chapter 5 and chapter 6, so let's review. We can write 2 equations, which is obviously FA cosine 30, FB will be 0 in the x direction, FC will be 0 in the x direction, and FD would be negative. And in a y, we will have FA sine 30 minus FB and plus FC. So again, we're back to chapter 5, which implies back to chapter 2. Easy stuff. But as you realize, we have 2 equations, but we have 3 unknown, FB, FC, and FD. We can solve for FD right away from the first equation, but we're still stuck in obtaining FB and FC from the second equation. And this is where the third equation comes in. So this is review, nothing new under the tree. The new thing here is sum the torques. But we've done this 2 weeks ago. This is a static equilibrium problem. Therefore, you can pick any point about which you want to calculate the sum of the torques. As we've seen, there is three ways for which the sum of the torque can be zero. Either F is zero, for us that's not very useful, or R is parallel to F, or R is zero. So obviously in this particular case we have four forces. So the sum of the torque will have four terms. The torque due to Fa, the torque due to Fb, the torque due to Fc, and the torque due to Fd. So three metrics would have to be set up. But since we are free to pick any point that we want, which point do you think would be useful to minimize the number of torques? If we calculate at A, if we calculate at B, or if we calculate at C? Ray suggests C. Absolutely. If we calculate it at C, then we know that the torque due to Fc and the torque due to Fd will be zero because R is zero. So this is where practice comes into play. You can make your life miserable by not picking an interesting point and have to calculate the torque of all the forces, or after practice you realize, okay, no problem, I'm just going to try to pick a point where there is either as many forces applied to, or a point through which as many forces, the line of action, go through. Either way. So in this case, if we pick it at C, obviously we only have to consider the torque due to Fa and the torque due to Fb. So we just have two metrics to figure out. The first one and the second one. Let's figure out the R vector. So all those will be about point C, which means that all our position vector will start at C. The first one will start at C and end where F is applied, which is point A. So our position vector is CA. So let's imagine that our coordinate system, which we haven't changed, but only translated, so that it's positioned at C. Now, as we try to express the position vector CA, very easy, it's just -10, 0, 0. Similarly, for the second torque, we need to figure out the position vector, which again starts at C, but this one needs to end where Fb is applied, which is point B. Therefore, we are concerned about CB, which is -4, 0, and 0. And that's it. Because really, the last row is from Newton's equation. So once we've done Newton's first two equations, let's just grab the information from there. What is Fa in componentation? Well, it's right here. Fa cosine and Fa sine. And the K is 0. What about Fb? Fbx is 0. Fby is -Fb. So again, all the information is in Newton's linear version of the first law. This is equal to the 0 vector. Remember, the torque is a vector. We know that in 2D, we're only going to pick up non-zero K. I and J will be 0. So really, this is 0K. So as we do the fish, the first term will give us -10 Fa sine in the K direction. The second one will give us plus 4Fb in the K direction, and this is equal to 0K. K is everywhere, therefore we can get rid of it. And the last equation is therefore -10 Fa sine 30 plus 4Fb is equal to 0. That's the third equation that we need. And that's it. 1, 2, 3. 3 equations, 3 unknown, the rest is math. Now you can solve for Fb from the last equation. You can solve for Fd from the first equation. You can substitute Fb into the second and then deduce Fc. And remember, as you solve for the system of algebraic equation, if you end up with a negative sign, two possibilities. You know that none of those results can be negative because what you're looking for is the magnitude of those concepts, which can be represented by vectors. And a vector graphically is an arrow. So as you look for the magnitude, you're looking for the length of the arrow. So it's gotta be positive. If it's negative, remember chapter 9, it means two things. Either you goof in the algebra, or you goofed in projecting your vector and adding them up in your X or Y direction. Or if everything here is correct, it means that the free body diagram is incorrect. Specifically, it means that the direction of that force is incorrect. So all you have to do is flip it. Or if you want to leave it, just make sure that at the end of your answer, if you see a negative sign, and you know that this refers to a force whose direction has been guessed, then you just say, oops, wrong direction. But make sure you mention it. Don't leave it as negative. That will take points off. Okay, because that would suggest that you don't have any understanding of what negative sign means. And if you're going to C270, those negative signs are going to be crucial. So we cannot ignore them. So if you're given a set of forces and you end up with a negative sign, then that means the problem gives you wrong direction for vectors, which is what I've done at the end of quiz 10, the last problem. But if you're coming up with a free body diagram, then one of them must have been a guess force. So all you have to do is go back and fix it.